Guys, welcome to another video. This time we're looking at chapter 9.3. This video I'm going to try to keep it as short as possible as we're looking at Young's double slit experiment, which we've briefly discussed. We've looked at this equation back in chapter 4. And we're going to go into a few more details here specifically about how Thomas Young himself, set up a double slit experiment, how you can set up a double slit experiment, as well as the importance of the double slit experiment to prove that light is a wave. This is very, very important right here, okay? And I almost guarantee that you will be tested on this in your examination one way or another. So let's begin. Okay, so how did Young set up his double slit experiment? And this was actually quite revolutionary because Young actually he actually bested Newton in some ways because up until before Young, it was thought or Newton had hypothesized that light was essentially particles or something close to that. Light is particles. So what Young essentially did with his double slit experiment was he said, that's wrong, and light is actually a wave. And he wasn't necessarily purposely trying to disprove Newton, but he was interested in the study of light. So a light is a wave. So this is what Young, or Thomas Young, had done. So he did it at a time before lasers were invented. So all he had was maybe probably like the old incandescent light bulb. So something like that, right? The old incandescent light bulb. And the old incandescent light bulb was interesting in the fact that it actually produced what are incoherent waves. And of different wavelengths. They're certainly incoherent. Oops, that's giving me a straight line. Okay, so these waves, the original light bulb didn't give off coherent light the way that a modern laser did. Okay, so how did he get around that? The first thing he did was that in terms of coherent waves, coherent means that the light sources are coming from ideally, they should come from the same source or the same type, and they need to have the same velocity, wavelength, and frequency. So in order to do this, the best way is to have a set digital laser that gives off a single light source, but he didn't have that. So what he actually did was he set up, in order to achieve coherent light, he set up a single slit diffraction. And this is important because, well, first off, you've just watched the video on single slit diffraction, and that allows light to be diffracted, okay, which is one of the properties of light. We'll get into that a little bit later, okay? So that light then goes on further. So it's almost like the light is coming from the same source, okay, which makes it coherent. And the monochromatic part, so monochromatic was he had to filter out this light, which was giving off all the different colors of the color spectrum. And so what he had to do was he had to filter that out using something like an orange filter here to give off only orange color light. And as a result of that, what he then was able to see was this is actually not quite our interference pattern. This is rather an intensity pattern. So actually, I'm going to erase this. So what he saw was an interference pattern. So he saw bright fringes of light like this. So he saw bright fringes of orange light like that, okay, that were equally spaced along the wall. Okay, and what we actually visually see is we see sort of a bunch of these little circles like this. Okay, and they're roughly equally spaced apart from each other. In the sort of the real version, the center one is a little bit brighter, so I'm just going to make it a little bit bigger, okay, to indicate that it is a little bit brighter than the other ones, okay, and they actually slowly sort of diminish in their intensity, which is what the original graph that you saw there was, okay? But what we're saying here is that that distance there is actually the same, okay? And that's what this is also meant to highlight here as well, okay? So two different ways to view that. So two important things to review. Monochromatic light, which is done using a filter, monochromatic, and the idea of a coherent light, which is done using a single slit. So single slit, coherent light. Coherent light, okay? A lot of the questions that you get, it'll almost automatically say if it's coming from a laser, you can assume it is monochromatic and coherent, or it'll specifically say a light source that is coherent and monochromatic. If it's not saying those things, then it is likely testing you about things, whether things are in phase or not. So it's testing on the concept of coherent or monochromatic. Okay, so what we were able to observe up until Jung was we were able to observe that light could be reflected. So something like a mirror, okay? Light could be refracted. So when you observe something underwater, okay, or something through a prism. Okay, so the famous photo that you'll see a lot of, right? White beam, and then it gets split up into all the different colors of red, and green, and violet. Okay, so the prism splitting light, that's refraction. Okay, and there's also diffraction of light. So light was observed to be diffracted, and this might have come possibly from a single slit. Okay, so when you observe light through a single slit, it is diffracting or it spreads out. Okay, so this was certainly observable. And the last thing that Jung did was, he knows that all waves also interfere. And this is what the double slit experiment essentially did, was in this original setup, he added this double slit and was able to successfully create an interference pattern. The most difficult part was actually because he actually had to, he didn't know at that time. What he actually discovered was that light is best able to create an interference pattern because of monochromatic light. So by adding the filter through using, again, the single slit, he was able to much more able to clearly show and demonstrate an interference pattern. And that was sort of the final pieces of Jung's puzzle, okay, was in using monochromatic light, okay, because an interference pattern was kind of observable without a light filter here, but it wasn't as clear, okay? So that is our first two learning objectives, okay, and let's get into the last one, which is a quick little calculation of S lambda capital D over little d. So very quickly, the slit distance here is little d. So it's usually quite small, so that's why it's little d. The distance between your double slit and the screen is big D, okay? It's usually a lot bigger, okay? This is measured in meters. This is usually measured in millimeters. And lastly, we have S. S is the distance between fringes. Distance between fringes. And as you can see in my diagram here, the fringes could be the center of the bright fringes. Okay, so this is the bright fringe. Would still be the same distance as the separation between the dark fringes. Okay, so it doesn't matter which one you measure from, it'll always be the same. So if you look back at this photo here, right, these distances here are all equal to each other. Okay, whether you go from this side, no matter how far out you go, okay, or if you go measure from the center of the fringes, those distances are also likewise exactly the same, okay? So you can take almost any measurement anywhere as long as you see the interference pattern. Lastly, lambda is our light source. So this is the wavelength of the light source. And what we're actually going to observe is that we're going to actually get red light when we complete our calculation. So Let's do that down here. So I'm going to rewrite the formula. Again, I always encourage you guys to do this is write the basic formula first. I think it was big D, yep, over little d. So write the basic formula. It just gets you familiar with it, okay? Without having to just copy it a bunch of times. We're trying to solve or prove that this is red light. Okay, so we were given all the other things. We were given this, this, and this, okay? And we're trying to show that, calculate what this wavelength is, okay? What is this guy going to be? So let's do a little bit of rearrangement. S little d over capital D. Okay, make your rearrangement and then do your substitution. So S is 7 millimeters, and then we have little d is 1 millimeter, and then we have big D, which is 10.5 meters. Okay, and I'm going to pull up my calculator here, so bear with me for a moment. We have 7 millimeters, 0.007 meters, essentially, times 1 millimeter, again, 0.001 meter. Okay, and then we're going to divide that by 10.5. And that's going to give me about 6.67 repeating, 6.6 repeating, 6 repeating times 10 to the power of -7. So a different way to write that is if we write this as 660, and then we can add 2 more decimals to this to -9. And what that really is that gives us 660 nanometers. And if you recall, the two ends of our visible light spectrum was, again, you should hopefully have this kind of somewhere in your brain by now, is you've got red light on one end and you have violet on the other end, okay? So red light should be pretty close, and that's what this is, okay? 660, pretty close to pure red light. And so that is our proof that the light itself was red. Okay, thank you guys for watching, and we'll see you next time in chapter 9.32.